Video topic, why humanity still can't reach Proxima. B, the nearest potentially habitable planet we cannot touch. On August 24th, 2016, a team of astronomers working with the European Southern Observatory made an announcement that stopped the scientific world in its tracks. After a 6-month observing campaign called Pale Red Dot, using the HARPS spectrograph at La Silla Observatory in Chile, researchers led by Guillem Anglada Escudé confirmed something that had been rumored for years but never proven: a planet orbiting Proxima Centauri, the closest star to our own sun. The planet, named Proxima b, sat right inside the habitable zone, the narrow band of space where temperatures could allow liquid water to exist on the surface. It was only slightly more massive than Earth, and it was orbiting a star just over 4 light-years away, practically next door in cosmic terms. For a few days, the news cycle exploded with the same electric question running through every headline. Had humanity just found its first real shot at a second home? But almost immediately, that excitement collided head-on with a brutal, humbling reality. Because right now, with every single piece of technology our species has ever built, we cannot reach it. Not even close. Not with rockets, not with anything currently sitting on an engineering drawing board. This is not some vague, far-off dream tucked into a distant, forgotten corner of the galaxy. This is our literal next-door neighbor, and we still cannot get there. Understanding exactly why reveals just how enormous the gap really is between where humanity currently stands and where we actually want to go, and by the end of this, you'll understand exactly what it would take to finally close that gap. Picture looking up at the night sky, knowing that relatively close, in cosmic terms anyway, sits a star with a planet that might genuinely be capable of supporting life. Now picture how frustrating it is to realize that even though this star is the closest one to us after our own sun, it remains completely beyond our reach with everything humanity currently has. The fascination with Proxima Centauri is not some random coincidence. Observations made using some of the most powerful telescopes and instruments ever built confirmed that this star hosts at least one potentially habitable exoplanet. It may genuinely have the right conditions to support life, or it could eventually serve as a future destination for human exploration and, further down the line, colonization. That turns this particular star from just another faint red dot in the night sky into something closer to a genuine strategic objective for the long-term future of our entire species. It stops being simple background scenery and starts becoming something we actively plan around, something engineers draw diagrams for, something scientists write funding proposals about, something that occupies real, serious institutional attention rather than existing purely as a curiosity for amateur stargazers. But the real question remains: given everything humanity has developed so far, is actually reaching it even possible? The short answer is no, not with today's technology. And unfortunately, the longer answer only makes things more frustrating. So far, humanity has not even managed to send a single human being past the moon, a destination sitting roughly 384,000 kilometers from Earth. And despite genuinely incredible achievements with probes like Voyager 1, the most distant object humanity has ever launched into space, we still have not truly left the immediate neighborhood surrounding our own solar system. Think about that for a moment. Humanity's single most impressive achievement in deep space travel, a spacecraft that has been continuously operating for nearly half a century, has still only barely poked its head past the outer edge of our own solar system's gravitational influence, nowhere close to genuinely interstellar territory in any meaningful sense. That single fact alone should tell you everything you need to know about the true scale of the challenge involved in reaching another star. Voyager 1, launched back in 1977, currently travels at roughly 17 kilometers every second, which works out to about 540 million kilometers covered per year. That is genuinely impressive by any normal standard. But at that pace, it would take somewhere around 76,000 years just to reach Proxima Centauri, and that assumes it was even actually heading in that particular direction, which it is not. To make a trip to this star realistically achievable within a single human lifetime, we would need speeds that go completely beyond anything we are currently capable of producing. The bare minimum realistic threshold sits somewhere around 10,000 kilometers per second. At that speed, we could reach Proxima Centauri in roughly 130 years, still a genuinely long stretch of time considering most people never actually live a full century. Push that speed up to 25,000 kilometers per second instead, and the travel time drops to roughly 50 years, which starts sounding a lot more reasonable. These are not arbitrary numbers pulled out of thin air. They come directly from the basic physics governing how long a spacecraft can realistically remain functional, how much radiation exposure onboard electronics can withstand over an extended journey, and how much degradation any instrument will inevitably experience across a multi-decade flight through the harsh vacuum of interstellar space. But we remain extraordinarily far from actually achieving that kind of speed with anything currently on the drawing board. This essentially means we have to completely abandon the idea of using conventional chemical propulsion, the same basic rocket technology we currently rely on to reach orbit and travel through the solar system. To reach even just 1% of the speed of light using that kind of propulsion, we would need something genuinely absurd, more than 1,000 trillion kilograms of fuel for every single kilogram of spacecraft mass. That would mean building a spacecraft roughly 100 times more massive than the entire planet Earth. 100 times more massive than the entire planet Earth. An amount of raw material that would essentially require dismantling several planet-sized bodies just to gather enough fuel for a single launch, which is obviously completely unfeasible under any realistic scenario. Just try to picture that for a second. A single spacecraft outweighing our entire home planet, sitting on a launch pad somewhere, theoretically ready to blast off using nothing but the same basic chemical combustion principles that power the rockets we already use today. The sheer absurdity of that image is exactly why virtually every serious researcher studying interstellar travel has already crossed conventional chemical rockets completely off the list of viable options. No matter how much we might improve efficiency or scale up individual rocket engines in the coming decades, that is exactly why the only real path forward involves investing heavily in entirely new forms of propulsion. And within that broader picture, we have to make a handful of genuine concessions along the way. For one, we essentially have to forget about sending actual human astronauts on this kind of mission, at least for now. A crewed mission would consume dramatically more resources, energy, and overall travel time compared to an unmanned alternative. An automated probe mission, by comparison, ends up far cheaper, considerably more practical, and genuinely achievable with current or near-future technology. Beyond the raw cost difference, there's also the simple matter of survivability. A human crew would need a fully self-contained life support system capable of functioning flawlessly for well over a century without any possibility of resupply or repair from Earth. An engineering requirement so demanding that most mission planners consider it effectively impossible with anything resembling current technology. A robotic probe, on the other hand, simply needs its instruments and communication systems to keep working, a considerably lower bar to clear. We can also simplify the overall goal itself. Rather than trying to actually enter orbit around Proxima Centauri or attempt a landing on one of its planets, we could instead simply fly straight through the system and collect valuable data during that brief pass. Even that alone would represent a genuinely enormous step forward for humanity, and it would save a tremendous amount of energy compared to attempting orbital insertion. A flyby mission also comes with a considerably shorter list of engineering headaches attached to it. No need to precisely decelerate a spacecraft traveling at a meaningful fraction of the speed of light. No need to design complex braking systems capable of surviving that kind of deceleration. And no need to figure out how a probe would actually settle into a stable orbit once it arrived. Simply flying through the system at full speed while collecting as much data as possible during that brief window turns an almost impossibly complex mission into something considerably closer to achievable. So, what propulsion technologies could actually get us there? One of the first options that usually comes to mind when discussing new forms of propulsion is the ion or plasma engine, technology that has already flown on several missions closer to home within our own solar system. These engines offer continuous, steady thrust over extremely long periods and end up far more efficient overall compared to traditional chemical engines. We also have nuclear thermal engines, which rely on onboard reactors to heat propellant gases and expel them with considerable force. But while genuinely interesting on paper, both of these technologies would still take more than 40,000 years to actually reach Proxima Centauri, which clearly is not nearly good enough for any realistic mission timeline. Both of these propulsion methods represent genuine, meaningful improvements over traditional chemical rockets in terms of raw efficiency, and both have already proven themselves reliable during actual missions closer to home, powering everything from small satellites adjusting their orbit to deep space probes conserving precious fuel over multi-year journeys. The fundamental problem is not that these engines fail to work. It is simply that even their impressive efficiency gains still fall drastically short of what interstellar travel genuinely demands. A 40,000-year travel time might as well be permanently impossible from the perspective of any single human generation, since no organization, government, or civilization has ever successfully maintained a continuous, coordinated project across that kind of timescale, let alone one requiring precise technical maintenance and monitoring the entire way through. A considerably more promising development comes from the VSIMR engine, short for Variable Specific Impulse Magnetoplasma Rocket, developed by the Ad-Astra Rocket Company under the leadership of former Costa Rican astronaut Franklin Chang Diaz. VSIMR is essentially a plasma-based engine with genuine potential for dramatically faster travel within our own solar system. For example, it could theoretically shrink a mission to Mars down from roughly 18 months to as little as 39 days, which is genuinely impressive on its own. That kind of dramatic reduction in travel time would completely transform how humanity approaches exploration and eventual settlement within our own solar system, turning what once required nearly 2 years of dangerous, resource-intensive travel into something closer to a routine, relatively short duration voyage. But even with that level of performance, it would still take somewhere around 2,200 years to actually reach Proxima Centauri. Better than earlier options, certainly, but still dramatically beyond the span of any human lifetime. It is honestly a genuinely bittersweet piece of engineering progress. Shrinking a Mars mission down to little more than a month sounds like something worth celebrating, and it absolutely is within the context of our own solar system. Yet the exact same technology, scaled up and pushed to its theoretical limits, still leaves us needing over 2 millennia just to reach our nearest stellar neighbor. It really puts into perspective just how enormous the gap actually is between traveling within our own solar system and traveling to even the closest star beyond it. This is where one particular project enters the story, and it is easily the most ambitious answer anyone has seriously proposed. In April 2016, just months before Proxima B's discovery was even announced, the physicist Stephen Hawking and the billionaire investor Yuri Milner unveiled a project called Breakthrough Starshot, backed by an initial $100 million in research funding. The plan sounds almost like science fiction, and in many ways it still is, but the underlying physics checks out. Instead of building one enormous spacecraft, the idea is to build an enormous fleet of thousands of tiny probes, each weighing only a few grams, roughly the mass of a paperclip, attached to an ultra-thin reflective sail only meters across. These featherweight probes would sit in orbit until a massive ground-based array of lasers, potentially generating something on the order of 100 gigawatts of combined power, fired a coordinated beam directly at their sails. That beam, pushing against the sail through radiation pressure alone, could theoretically accelerate each tiny probe up to roughly 20% of the speed of light within just a few minutes. At that velocity, the journey to Proxima Centauri would take only around 20 years, an almost unbelievable improvement over the thousands of years demanded by every other propulsion method on the table. Since these individual probes would be extraordinarily small and inherently fragile by design, the overall risk of a catastrophic collision with stray interstellar dust particles along the way would honestly be fairly significant. But the Starshot project effectively compensates for that particular risk purely through sheer numbers. By launching an entire fleet of several thousand individual units simultaneously, even if a considerable number fail to survive the full journey intact, a meaningful number would still realistically complete the mission successfully. It is essentially the same underlying logic used by nature itself across countless biological systems, redundancy and sheer volume compensating for individual fragility, an approach that trades the comforting reliability of a single heavily armored spacecraft for the statistical resilience of an entire dispersed fleet, any one of which surviving the journey would count as a genuine historic success on its own. Each individual probe would also come equipped with its own compact laser-based communication system, specifically designed to send scientific data all the way back to Earth, across that enormous interstellar distance, a signal that would then take another 4+ years just to arrive, given the sheer distance light itself has to travel. What makes this particular project genuinely impressive is that something that sounds almost entirely like it belongs in a science fiction film could realistically become genuine reality within the next couple of decades, provided it continues to receive the necessary ongoing funding and institutional support. Several early-stage prototype tests have already been quietly conducted here on Earth, including small-scale laser propulsion demonstrations and early sail material testing, each one gradually chipping away at the individual technical hurdles, standing between the current concept and an actual, fully operational interstellar mission, ready for genuine launch. None of these early tests guarantee eventual success on their own, but they do represent real, tangible progress, rather than pure speculation confined entirely to a whiteboard somewhere. With sufficiently strong investment behind it, we could realistically see this exact mission actually launched and executed within our own current generation. And who knows, we might even end up witnessing the very first real photographic image ever captured of a planet orbiting an entirely separate star system. It is genuinely difficult to overstate what that single image would mean for humanity as a whole, comparable in many ways to those first grainy photographs sent back from the surface of the moon decades ago, except this time the subject would sit not a few 100,000 kilometers away, but across an almost incomprehensible gulf of interstellar distance that no previous generation of humans ever had any real hope of crossing. It's worth pausing here on what we actually know about the destination itself, because the picture has grown more complicated since that first 2016 announcement. Proxima b orbits its star every 11.2 days, sitting roughly 7 million kilometers away, just 5% of the distance between Earth and our own sun. It's estimated to be only slightly more massive than Earth, likely a rocky world, and it sits comfortably inside the habitable zone where liquid water could theoretically exist. But being in the habitable zone and actually being livable are two very different things. Proxima Centauri is a red dwarf, and red dwarfs are notorious for violent, unpredictable outbursts. In May 2019, astronomers observing the star recorded a superflare so powerful that Proxima Centauri briefly brightened by a factor of 14,000 times its normal level in ultraviolet light, an eruption so intense that if a similar event struck Earth, it could seriously threaten the ozone layer. A planet sitting as close to its star as Proxima b does would take the full, unfiltered force of blasts like that on a regular basis, stripping away atmosphere over time and bathing the surface in radiation far beyond anything life on Earth has ever had to contend with. Whether any atmosphere could survive that kind of relentless bombardment, or whether a strong enough magnetic field could shield the surface the way Earth's does, remains one of the biggest open questions hanging over the entire system. And Proxima b is not alone out there anymore. In 2020, researchers reported hints of a second, larger planet in the system, tentatively named Proxima c, sitting much farther out on a wide, multi-year orbit, though its existence has since been disputed, with some scientists arguing the signal may be an artifact of stellar activity rather than a genuine planet. Then, in 2022, a third and much smaller world was confirmed. Proxima d, a planet only about a quarter the mass of Earth, orbiting so close to the star that it completes a full lap in just 5 days, making it one of the lightest exoplanets ever detected using the radial velocity method. None of that changes the fundamental math of the journey, but it does mean that whatever we eventually send toward Proxima Centauri, whether a fleet of Gram-sized probes or something far more advanced, won't just be visiting one planet. It will be arriving at an entire miniature solar system of its own, one we still barely understand. Even if we ultimately do not discover lush, fictional worlds resembling something straight out of a science fiction movie, or find any confirmed evidence of alien life whatsoever, a genuine mission to Proxima Centauri would still carry an almost immeasurable amount of scientific value all on its own. It would allow researchers to closely study planetary formation processes actually unfolding inside an entirely different star system, directly compare those observed processes against our own solar system's formation history, and ultimately develop a considerably deeper understanding of how our wider Milky Way galaxy genuinely functions as a whole. Every single planet we have ever managed to study up close, whether inside our own solar system or somewhere far beyond it, has taught us something genuinely unexpected about how planets actually come together, evolve over time, and occasionally end up habitable or completely hostile to life, depending on countless small variables that were never fully predictable in advance. A planet as close, relatively speaking, as Proxima b represents an absolutely unique opportunity to test every one of our current theories about planetary formation against real, physical, close-up evidence, rather than relying purely on distant telescope observations and mathematical modeling alone. As one famous astronomer once pointed out, by the time humanity is genuinely ready to visit other stars, we will inevitably no longer be quite the same species we are today. Our civilization as a whole will need to have matured considerably in order to pull something like this off successfully. Only a genuinely wise, resourceful, and technologically capable civilization would ever prove capable of facing down and eventually overcoming the truly immense emptiness separating individual star systems from one another. If humanity genuinely intends to survive over the long term, continue thriving as a species, and leave any kind of lasting, meaningful mark on the wider universe around us, we ultimately need to look well beyond our own small, familiar blue planet. History has repeatedly shown that civilizations which stop actively pushing their own boundaries outward eventually tend to stagnate. And there is a compelling argument to be made that a species confined permanently to a single planet, no matter how comfortable that planet might currently feel, remains fundamentally vulnerable to any single catastrophic event capable of threatening its entire existence all at once. Spreading outward, even gradually, even imperfectly, represents a genuine form of long-term insurance for humanity as a whole, one that simply cannot be achieved by staying permanently confined to the world we currently call home. Reaching toward the stars is never really just about simple scientific curiosity for its own sake. In a very real sense, it increasingly starts to look like something closer to an existential necessity for our long-term survival as a species, and Proxima Centauri, sitting there with its own genuinely promising world quietly orbiting nearby, could very realistically end up serving as the true first step in that much larger, far more epic journey still waiting ahead of us. It is a strange thing to sit with, that the answer to one of humanity's oldest questions, whether we are truly alone out here, might genuinely begin with nothing more dramatic than a swarm of Gram-sized probes silently drifting past a single rocky planet 4 light-years from the world that built them. The underlying technology certainly is not fully ready just yet, not by a long shot, but the genuine desire, the sheer determination, and the raw courage required to actually attempt something. This ambitious, those particular qualities already sit firmly embedded within who we are as a species. The only real remaining question left standing is whether humanity will ultimately find the sustained determination necessary to eventually turn this ambitious dream into an achievable, lasting reality. Every single major achievement in the entire history of human exploration once looked exactly this impossible, right up until the precise moment someone actually managed to accomplish it. And there is no obvious reason to assume reaching another star will end up being any fundamentally different, provided enough patience, funding, and generational commitment eventually gets thrown behind the effort. Somewhere out there, 4.2 light years away, a small rocky world keeps circling a faint red star every 11 days, waiting for whatever it is we eventually decide to send its way.